Let me introduce to you Laura Capelli, or she just moved up at the speaker side. She's assistant of associate professor at the Politecnico University of Milano, Italy, and presenting here a speech on micrometeorological methods. Please, Laura.
Thank you very much. Yes, thank you very much. Today, this afternoon, I will speak about, we'll discuss with you about the possibility to use micrometeorological methods for the indirect quantification of Odour emissions. Well, we've heard several times now that the quantification of Odour emissions from complex sources is difficult. And this includes, for sure, Odour emissions from passive area sources. The ways there are, let's say, two approaches that can be used to quantify Odour emission. The first one is the use of direct methods, which basically involves the use of wind tunnels, flux chambers, which can be used to measure Odour concentration and then calculate Odour emission rates. Or there is also the possibility to use indirect or so-called micrometeorological methods. Direct methods have always been the preferred way, historically, to measure emissions, Odour emissions on passive area sources. But because of their apparent simplicity, but they are not so easy, indeed. There are still some open issues. This has been long debated during the revision process of the EN 13725, and in the end we didn't come up with a unified solution because we realized that the parameters affecting the sampling with the hood systems are really many. And also there is an intrinsic problem when trying to sample very large emissions like landfill areas, because in that cases the surface covered by hoods is very small compared to the emitting surface. So indirect methods are methods that are based on analytical and semi-empirical equations that allow to estimate the vertical flux of a passive substance emitted from a source based on concentration measurements at various distance from the source by combining them with the meteorological conditions. As I mentioned this morning, these methods are mentioned very often in the scientific literature as an alternative to direct methods, but their practical applications, at least as far as others are concerned, are really very rare. However, they are becoming interesting again because the instrumentation that is needed for their implementation is becoming more reliable and affordable. I'm speaking of sonic anemometers, for instance, that now have a cost which is below 10,000 euros, more or less. So micrometeorological methods can be grouped into, include a variety of different methods. Let's say we could start with the methods based on the Money-Nabokov similarity theory, like, for instance, the flux gradient method, or also methods based on the definition of turbulent flux, which include the primary method is the Eddy covariance method, followed by all its derivations, like the disjunct Eddy covariance and so on. And then there are also inverse dispersion modeling techniques that however, have some limitations if applied to others that we will discuss in a few moments. What is, in principle, a micrometeorological method? The definition is very simple, indeed. It is a method that, based on the instantaneous measurement of the three components of the wind speed, the friction velocity, and the turbulent flow of sensible heat, and the Money-Nabokov length, which are all things that can be measured by a triaxial sonic anemometer, enabled to calculate the flux of a passive chemical species by this apparently simple equation here. What are the general characteristics of these methods? They are relatively reliable, meaning that the literature is full of examples of applications in agrometeorological meteorology for the determination of greenhouse gas fluxes, for instance. They are applicable only to extended sources, ideally infinite sources. So they provide an emission rate per unit surface, what we call the specific Odour emission rate in terms of Odour emissions. They are applicable for measurements that are carried out directly on the source. And this is particularly interesting because if we think about the application to odor concentration measurement, we know that measuring odor concentration in ambient air is often a tricky issue because we deal with very low odor concentration values that are hardly measurable. Whereas when measuring close to the source or directly over the source, then the odor concentration is more easily measurable, which is the main difference with inverse dispersion modeling, which requires measurement downwind from the source. Their mathematics is relatively simple, and they do not require the construction of the three-dimensional wind speed. So they only require local micrometeorological measurements for their application. The question here is, okay, fantastic, these micrometeorological methods are applied for the estimation of greenhouse gas fluxes. Is it possible to apply them also to the measurement of other emissions? To answer this question, it is first necessary to study, as usual. You have to study what these methods are, how they work, on which principles they are based. Then try to ask yourself, what are the features of the instrumentation required for their practical implementation? Then the third question is, let's try to make some preliminary evaluations of applicability by means of simulations with real data. So before going into the field with expensive instrumentation, it's worth spending some time in simulating what type of data you are expecting. So let's start with the study of the method. The main method, or the original micrometeorological method, is the Eddy covariance. It is, in principle, a very simple method. Once you have a 3D sonic anemometer, which measures the variables that I mentioned before, and you have a fast analyzer of the concentration of the species under investigation, you may calculate the vertical flux of the substance almost directly with this expression. Unfortunately, things are not so easy as they look like, because first, the analyzer should have particular characteristics. First, it should be able to carry out the measurement within the measurement volume of the sonic anemometer, exactly that volume. Second, it should be able to measure the concentration at the same frequency of the anemometer, which is typically in the range of 10 Hertz. So we understand that it becomes not banal anymore. And that is exactly the reason why, also for agrometeorological meteorology, other methods have been derived from the original Eddy covariance method. One method is the Eddy Accumulation. This works on a different principle. In practice, for each time instant, a small volume of air, which is proportional to the absolute value of the vertical component of the wind speed, is sent to a sampling reservoir, depending on the sign of the vertical component of the wind speed. It can be proven by remanaging the equations that in this case, the vertical flux can be obtained like this. And this is still quite a relatively simple equation involving the average vertical wind speed and the difference of concentration measured in the two sampling reservoirs. However, the problem here is the fact that you have to send a small volume of air that has to be proportional to the volume, vertical component of the wind speed, which requires the use of very particular valves. So the relaxed Eddy accumulation method is a further simplification of the method in which the sampled volume of air doesn't need to be proportional to the absolute value of the vertical component of the wind speed, but it can be constant. This requires the introduction of another constant, this constant be a semi-empirical constant, to be introduced in the equation for the calculation of the vertical flux. But also in this case, we can see that the method is, in the end, based on the measure of a difference in concentration in two sampling reservoirs. So it's all a problem of measuring delta C. So in the end, it's a problem of instrumental resolution. We don't have much time today. We're very late, so I will not go into the details of the practical implementation of these methods, but if you look also at the paper that I shared, there are different methods to evaluate the correct value of B, to introduce deadbands to improve the measurements. But it is important to evaluate the minimum instrument resolution required for the implementation of this method. The second method that is particularly interesting is the gradient method. The gradient method is based on the Monin-Obukhov similarity theory. Monin and Obukhov are two men that are well known to people who do dispersion modeling. They have formulated an amazing theory that proves that the vertical profile of each characteristic variable of the surface layer, when suitably scaled and made dimensionless, can be expressed by a universal function, which depends exclusively on the stability parameter. And the consequences of this theory are very interesting. They can be reformulated like this, and the vertical flux, so the emission rate, can, in this case, be expressed by this expression here, which looks complicated, but it isn't. Again, it is a problem of measuring a difference of concentration, in this case, measured at two different measurement heights. So it's based on the idea of measuring a gradient of concentration between two different heights. All the other parameters can be considered as known. These are universal functions which have been defined in the recent literature. So expressions for these universal functions can be found for different stability conditions. I skip this because otherwise it becomes too long. What I wanted to conclude is to share with you some preliminary results, because as I said, we tried to figure out, is it possible to effectively apply this measure for odor concentration measurement? So we did a simulation. We used real data, real meteorological data measured from a sonic anemometer in Rome, in Tor Vergata, for the year 2015. We, in this case, hypothesized to know the emission flux. And what we tried to simulate is, given the emission flux, given the meteorology, what are the difference of concentration that we expect in the case of the relaxed eddy accumulation methods in the two reservoirs and in the case of the gradient methods at the two heights? Are we capable of measuring such concentration differences? Well, for the case of the relaxed eddy accumulation, you can see that out of 1 year of data, the number of measurements, let's say, in which the difference of, assuming a specific odor emission rate of 1 odor units per square meter per second, the number of, which is a value that has been taken from databases of our lab, and it should be representative of a quite odorous passive area source. But we can see that the number of data which present a difference in concentration above 50 odor units per cubic meter is negligible, is below 0.1%. Now, to be very honest, who works with olfactometry knows that measuring difference of concentrations below 50 odor units per cubic meter starts becoming quite difficult. So the conclusion is probably this method is not good for being applied to direct odor concentration measurements. Let's look at the situation with the gradient method. We assume to use these two measurement heights to place one measurement system at 0.5 meters. the second one at 10 meters. Again, we assume to have an odor flux of 1 odor units per square meter per second, and we can see that here the situation is quite different. We have about 44% of the data which present a difference in odor concentration between the two heights above 50 odor units per cubic meter, which and 30% of data being above 100 odor units per cubic meter. One part of the data could be potentially measurable with the odor concentration measurements. Of course, the problem is for really applying such methods, it would be needed to make further investigations and simulations to specifically evaluate if the method is effectively applicable in the specific situation. So as you can see, that these are very preliminary results, but I wanted a little bit to illustrate our thoughts on these potential future application of micrometeorological methods. Based on our research, we concluded that the only two methods that would be theoretically applicable to odor measurements are the relaxed eddy accumulation and the gradient method. Although, as we have seen based on the simulation, in the end, probably only the gradient method is really applicable to odor concentration measurements. A standardization of the experimental facilities is needed for the implementation of such methods. There are no clear indications about what to use, especially if we don't refer to greenhouse gases, but to VOC measurements. The main limitation to their application is still the application of the direct measurement of an odor emission rate is still related to the resolution and accuracy of the instruments that are available for the measurement of odor concentration. So specific evaluations should be carried out to be able to evaluate accurately the minimum accuracy and resolution requirements for potential odor analyzer to be used for such application. However, the last word is not said, we say in Italy, because there can be further implementation which might make this method effectively applicable in the future. Thank you for your attention, and I leave you to the coffee break.
Thank you, Laura, who showed us you can be a very clear speaker even wearing a mask.
Oops, sorry. I forgot that I could. In Italy, we are so used to wear masks always that I'm just used to that.
It's our destiny at the moment, speaking with a mask. Okay. The organization, I look at the organization. Carlos, can you tell us a question for Laura? Are there questions for Laura?
No question. Ton.
Question? Do you have a microphone? Is there a microphone?
Thank you for this idea. It's not so much of a question, but I remember one of the first projects I did about 40 years ago with pig slurry and with a team from England and from the Netherlands, and we had to make circles of pig slurry, then measure the turbulence, and that resulted through some calculation that escapes me now in one specific characteristic height at which you could sample and then do the math. And we spent several months doing that, and there are publications, but I just wanted to mention it because we did a lot of work at the time, and maybe that's a third method which looks very similar to the Monin-Nabokov way. So I just wanted to mention it, and I'll send you.
I think I saw these publications during all our extensive literature search. It should be said that compared to 40 years ago, the awareness about how to treat meteorological data has changed a lot. So some things that were strange, but not only 40 years ago, I would say also 20 years ago, have been understood differently. For instance, the universal stability functions, the publications regarding the formulations of the universal stability functions for stable conditions are of 2020.
Yeah.
So there are some pieces that were missing, and I think now we are at a point in which apparently some things have been understood, and we can try to investigate if there is the possibility to carry out new experiments and see if we are able to get something out of it. I'm not sure this is possible, so I'm not saying I'm sure this is a possibility, but I think it's worth investigating.
I think it's a very valuable direction to explore, so good idea.
Okay. Yeah, there's another question.
Thank you for your nice presentation. My question was regarding the distance from the source. So you started by saying that some of these approaches were defined for an infinite source. So have you explored or...
The distance from the source should be 0. So the measurement should occur on the source or at maximum at the boundary of the source. So it is not foreseen to make the measurements downwind. So the distance must be 0 for micrometeorological methods. Otherwise, you have to go towards reverse dispersion modeling logics, which are similar but still quite different.
Because some of these studies using this kind of methods, for example, exploring heterogeneity in heat fluxes or latent fluxes inside urban areas. So they take some distance from, finally in city you have different neighborhoods with different morphologies and hence different fluxes, and they take some distance to take homogeneity. But yeah, of course, if your source is more,
absolutely,
you have to be
there are a lot of studies regarding downwind measurements at some distance from the source, but they use a different logic. They are not based on the gradient method or on the Eddy covariance method, which really are based on a different logic. So this is still a possibility, a very interesting possibility indeed. However, my doubt is that if the idea is to go towards other concentration measurement, the more you get far from the source, and the more it becomes difficult to obtain measurable data in the end.
Thanks.
This is very complicated but very important. Fugitive emissions are always a problem. I was wondering, one of these methods that you might have considered or looked into, the tracer method, where you just launch a tracer and you measure downwind. You don't need inverted dispersion modeling, but just compare it. Is that something you've looked into? What is your opinion on that? Because
that is a very good question, meaning that my idea, not yet well formulated in my mind, so I cannot formulate it here, but my idea is to go towards a sort of combination of tracer method with this type of methods, and I think this could really help in getting a solution. But yes, of course, tracer method is also a possibility.
Yeah, especially because a lot of the times you don't know where the source is, or there may be multiple leakages or sources that you don't know, and so that might have some advantages. But I have never used it, but we're currently looking into methods for leaking detection at digester facilities for methane leakages.
Yes, absolutely. This is
reconsidering
also,
London, I guess, yeah.
and this is also a potential development in this direction. So here it is about investigating different options